welcome. Welcome to Perimeter Institute's Mike Lazaridis Theatre of Ideas here at Perimeter Institute in Waterloo, Ontario, Canada. And welcome to this Perimeter's public lecture series presented by BMO Financial. My name is Greg Dick. I'm the Director of Educational Outreach here at Perimeter, and it is a pleasure to welcome everyone here this evening. And also a special welcome to those of you watching online. Now, the lecture itself will last approximately 1 hour and will be followed by a question and answer session. For those of you watching online, Dr. Kelly Foyle and a team of PI researchers are behind their keyboards, ready to engage in answering any questions that you have throughout the lecture, both from the Facebook and the Twitter feeds. If you want to do that, please use hashtag PI Live. And I will also take a question or two from the Twitter feed at the end for the guest speaker. So if you want to get your question, get it in early so it has time to make it all the way to my phone. And now, it is my pleasure to introduce tonight's very special guest speaker, Dr. James Weatherall. Dr. Weatherall is a professor of logic and the philosophy of science at the University of California, Irvine, and would describe himself as a physicist, a mathematician, and a philosopher. His main research interests lie in the mathematical and conceptual foundations of classical and quantum field theories, but also works on issues of general philosophy of science with a particular interest concerning building models to finance. In addition to his academic work, Dr. Weatherall has written on physics, philosophy, and finance for numerous magazines and newspapers, including Scientific American, the Financial Times, and Slate. And he has also written 2 books, most recently, Void, The Physics of Nothing, and, of course, The Physics of Wall Street, the topic of tonight's lecture. So please join me in welcoming to the stage to discuss how ideas have moved from physics to finance with his talk, The Physics of Wall Street, Dr. James Weatherall.
Thanks very much. Thank you, Greg. And thanks, everyone, for coming. It's a great honor to have been invited to speak in this distinguished lecture series. I'm very happy to be here. So I'd like to begin with a little warm-up exercise. So maybe some of you have heard of this before. If so, bear with me because there's a point. But for the rest of you, it's going to get those juices flowing. Okay, so this is a probability puzzle that is inspired by an old game show called Let's Make a Deal. It was on TV in the US, at least from throughout the 80s, the 70s and the 80s. And contestants would be brought up on stage, and they'd be given various challenges or given the opportunity to play various games. One of those games so the host, Monty Hall, would present a contestant with 3 doors. Behind one door would be a brand new car. Behind the other 2 doors would be goats. And so you were given the opportunity to choose a door. If you chose the door that had the car, you of course won the car. Otherwise, you won the goat. Now, the contestant would choose a door, but then there would be a twist. Monty Hall would go and open another door, always revealing a goat. He would then offer the contestant a choice. Should you stick with the door you started with, or should you switch to the last remaining unopened door? Now, before I say what you should do, let me give a little bit more history, because this problem became famous in the early 1990s in connection with a newspaper column written by a woman named Marilyn Vos-Savant. So Marilyn Vos-Savant, her claim to fame is that she holds the Guinness Book of World Records record for highest IQ ever measured. So, she'd write a column. You could write letters in and ask her for advice. And so, questions like, should I change jobs? Should I leave my husband? Things like that. The smartest woman in the world would weigh in for you. So someone wrote in with this problem. And Vos-Savant answered the question in a column and said, you should always switch doors. Now, the response to this was overwhelming. Thousands of people wrote in, including ordinary readers, but also people with PhDs, faculty positions in fields like physics and statistics, mathematics, computer science, saying things like, "You are the goat." That was one of the letters that was published. Also saying things like, look, the state of innumeracy, right, illiteracy about numbers in the public at large, is such that it is irresponsible for someone in a position of influence like yours to spread this kind of nonsense. Obviously, it doesn't matter what you do. There are two doors. You don't know which one the car's behind. 50-50 chance. Literally thousands of letters written saying this. Savant wrote another column, publishing several of these letters and addressing the comments and explaining her reasoning in more detail. Again, the letters poured in. She wrote a third column, and that's where it ended. So, what should you do? You should switch. You should always switch. Now, this is a problem that a lot of people, including the experts, don't get the first time they see it. Now, if you're feeling a little uncertain about this advice, I advise you to go home and play the game with your friends. Just do it over and over again and see who wins most often. You could also, write some computer code and try simulating it, or you can do the calculations yourself. However you want to test this to convince yourself, you should always switch. There's an easy way to see it, which is that to begin with, there are three doors. You really don't know where the car is. There's a 1/3 chance, whichever door you pick, that you'll be right, a 2/3 chance that you'll be wrong. So when Monty Hall opens one of the doors and then gives you the option to switch, what he's doing is giving you the option to bet that you were wrong to begin with. But of course, there's a 2/3 chance that you were wrong to begin with, and so that's a bet you should take. Okay. Let's move on. Keep this in mind, though, because this is going to come up again at the end of the talk. So let me say a little bit more about the perspective I have here. As Greg said, I teach philosophy. I have a background in physics and also in philosophy. And I may be not the person who you would normally expect to be giving a lecture on finance. I came to this problem, or I came to this field to be interested in finance in 2008, in the fall of 2008, a time when I think a lot of people sort of woke up to start thinking about finance. As any of you old enough to have a checking account will know, the global financial system collapsed that fall. Now, at the time, I was a graduate student. I was a graduate student in physics. I was working at a university in Hoboken, New Jersey, right across the river from Wall Street. Many of my friends, either both from grad school and from undergrad, had gone to work on Wall Street, many of them with backgrounds in the sciences. And so as all of this was happening, I began tuning in, and my attention was attracted in particular by a number of articles that claimed that there was a relationship between the financial crisis and physics. In particular, there was the claim that over the previous 30 or 40 years, physicists had moved to Wall Street in large numbers and had changed the way the world financial system worked. They had done this by introducing sophisticated or complicated, at least, new mathematical methods, new financial products that were based on those mathematical methods, and had created a system that was far too complicated for anyone to understand. And moreover, had done so by committing a kind of fatal error. They had imagined that markets, composed of ordinary human beings, people who are irrational and who make decisions for all sorts of reasons that aren't governed by laws the way that physical systems are, could somehow be treated or modeled or explained, or their behavior could be predicted using mathematics. And the authors of these articles would often say that was clearly insane. Now, I was interested in this for a number of reasons. One reason I was interested in this was as a physicist, I thought, well, it was people like me who did this. And so I wanted to understand better what, in fact, the contributions of physicists had been. How was it that physicists had come to have so much influence in finance, as these articles suggested, that they were in a position to cause such calamity in the first place? And then secondly, I wanted to understand whether there was any value to the kinds of contributions that were being made by physicists. I wanted to understand what they were trying to do, whether they had succeeded, where things had gone wrong. And so, in part, I was approaching this problem as a philosopher of science. This was a place where people were using methods from the sciences to study an area that was pretty far from physics. And I wanted to understand what the methodological issues that had arisen were. And in part, it was just, I wanted to understand what had happened. Okay, so the talk today is going to cover three questions that I think come out of this work. The first question is essentially a historical question. It's a question about how, in fact, physicists came to make influential contributions to financial practice. So I'm going to tell part of the story. There's more to the story, of course, but I'm going to focus on some of the key bits that I think are helpful in understanding how this happened, and also, I think, helpful in understanding what the goal was and what was accomplished. I'm then going to ask a somewhat different question, which is whether or not physics can continue to provide novel insights into financial markets. And here I'm going to point to a more recent example where I think deep insight into the structure of markets has come out of an analogy with physics, an understanding of how systems in physics work. And then finally, I want to step back and ask this somewhat more philosophical question with these examples in mind of how we should understand the status of mathematical models in finance that have been introduced by physics. And in particular, whether the kinds of criticisms that were being repeated over and over in 2008, that you still hear sometimes now, and that in fact began appearing as early as 1987. So every time there was a financial crisis starting around 1980, you would see someone writing these op-eds about how physicists were to blame. So this is a theme that's come up over and over again. I want to address that issue in conclusion. Okay, so sort of big picture overview of what I'm going to do. I'm going to start with the history, then move on to a contemporary issue, and then conclude. Okay, so the story I want to tell begins with World War II. In particular, it begins with the Manhattan Project, which of course was the program to build a nuclear weapon in the United States. Now, what happened during World War II was that a very large fraction of the physics community, both theoretical and experimental physics community, in the United States and in allied countries, was brought into the war effort. They were brought to sites like Los Alamos, some other facilities, a facility at the University of Chicago, in Hanford, Washington, Oak Ridge, Tennessee, and they were asked to collaborate with one another on a big project, right? Doing a lot of theoretical and experimental work to bring nuclear physics to a certain level, and then using that knowledge to build something. Now, in 1942, when the Manhattan Project really got going, one of the things that they hoped to do was use plutonium as the fissile material in a nuclear weapon. Now, plutonium had been isolated as an element only a few months before this. It had been produced in a nuclear reactor at the University of Chicago in minuscule amounts for the first time very shortly before. The hope was that somehow this experimental new process, this new material that had never been known to Earth before, could be produced in large enough quantities to actually build an arsenal. And it had to be done quickly enough to make a difference to the war effort. So how do you do that? I mean, this is the kind of thing that really hadn't been done before. Almost. It had been done at least once before. And in fact, it had been done just a few years before in private industry, essentially for the first time. It had been done by DuPont. It had been done by DuPont in the production of and commercialization of nylon. So nylon was produced by a lab internal to DuPont, focused on doing basic research in polymer chemistry, so fundamental research, in 1935. Again, it could be produced in only minuscule amounts, but it was immediately recognized that as a synthetic fiber, it had all of these properties that were clearly marketable, highly commercializable, and needed to be produced. I mean, could be produced for profit. And so DuPont endeavored to figure out a way to take this cutting-edge research and turn it into a product as quickly as they could. And the strategy that they adopted, which was entirely novel at the time, was to do everything at once. So rather than wait for the theorists and the experimentalists who were just beginning to figure out how to make this stuff, before waiting for them to finish all of their work and all of the research that they wanted to do, before waiting for the sort of next level of industrial scientists to do the tests that they would want to do before designing the factories, before waiting for the engineers who were going to design the factories to figure out how much they could actually make and what the costs would be and so on, before waiting for the marketing people to figure out how they're going to sell this, they got everyone involved all at once, asking everyone across this whole hierarchy of different parts of the commercialization chain to interact with one another and collaborate. And over the course of 5 years, they managed to take this minuscule amount of experimental material that had never been produced before and turn it into a product that was able to sell 7 million units in the first week and 40 million units in the first year as women's hose. Leslie Groves, the general in charge of the military side of the Manhattan Project, when he realized what needed to be done to produce plutonium, went to DuPont and hired the exact same team of people who had produced nylon and asked them to make him his plutonium. And so DuPont was responsible for designing the first prototype nuclear reactor in Oak Ridge, Tennessee, and then the major reactor in Hanford, Washington, that produced the plutonium for the early nuclear weapons. The strategy that they adopted was the same as the strategy that they had used for nylon, which meant that this large number of theoretical and experimental physicists working on in Los Alamos and other labs on the basic physics side of the Manhattan Project were asked to collaborate all the way up the hierarchy. They were asked to weigh in before the research was even done on questions like, how do we actually build this reactor? On questions like, what are the strategic military uses of this sort of weapon? How should we think about applications? This changed the culture of physics in the United States. After the war, there was a much different attitude, both among physicists themselves, within the government more generally, and I think in society more generally, concerning what sorts of things physics could contribute to. And there were practical consequences to this. So one practical consequence was that much more science funding across North America and Western Europe was tied to defense spending. One had to justify your basic research in terms of its applications, in many cases applications to the military. Another change was that there were many more scientists who were working in government labs. And working in government labs, not just on particular defense projects, but who were paid by the government to work on whatever they wanted. So one example of someone who had this kind of job, who had worked in the Naval Research Laboratory in Washington, D.C. during the war, studying the acoustic properties of undersea explosions, was a man named Maury Osborne. Now, this is Maury Osborne right here. Maury Osborne was a kind of polymath. He was interested in everything and was able to apply methods from physics to an enormous range of problems. So for instance, he has a paper in which he explains why bumblebees can fly. Now, this was, in fact, a major open question in entomology in the 1950s because, I mean, think about it. Bumblebees have got these big fat bodies, got these little wings, and somehow they're buzzing all over the place. It was a puzzle how this could possibly happen as a matter of aerodynamics. Osborne treated it as a problem of physics, not a problem of entomology, presented a solution and published it. He had a paper on salmon migratory patterns, where he treated salmon as little submarines and tried to calculate the efficiency of their propulsion systems by looking at the difference in their weight before they got into their rivers and when they got to the spawning grounds, and so on. He worked on all sorts of things, and his job at the Naval Research Lab not only permitted this, but encouraged it. In fact, his only obligation at the Naval Research Lab was to be a kind of internal consultant. He could work on whatever he wanted, as long as he was willing to answer questions when other researchers at the facility came and asked them. Okay, and so one of the many things that he decided to work on was financial markets. Now, he came to financial markets in the same way that I think many people do. He had 10 children. When numbers 9 and 10 were born, they were twins. He thought, I could stand to make more money. And he thought, I've heard people make money in the stock market. Perhaps I could make money in the stock market. And so he decided that he was just going to go and figure out how to invest, in the same way that he'd figured out how undersea mines work, how bumblebees fly, how salmon swim. So this is a passage from the paper that he published the following year, in 1959, called Brownian Motion in the Stock Market. He writes, let us imagine that a statistician, trained perhaps in astronomy and totally unfamiliar with finance, is handed a page of the Wall Street Journal containing the New York Stock Exchange transactions for a given day. What would he do? I mean, this is in fact what happened. I mean, it's just autobiography. He went and bought the Wall Street Journal and laid it out on his kitchen table and thought, well, what am I going to make of this? Well, what he found when he opened the page was a whole lot of numbers. It was a data stream, something that he knew how to analyze. He could think about it the way that he would think about data coming in from the experiments that had happened during the war, from the astrophysical experiments or observations that he had done as a graduate student, so on. So he just started performing statistical tests. He just looked at how these things were distributed, looked for correlations, tried to find anything that he could. And he realized that there was a pattern in the data. It was a pattern that was familiar from elsewhere in physics. So let me back up a little bit. This right here is a Scottish botanist by the name of Robert Brown, who was active in the early 19th century. Brown is famous for having observed that when you look at little particles of pollen suspended in water, they jitter. They don't stay stationary. He described this jittering of pollen particles, and it's taken his name. It's now called Brownian motion. Much later, Einstein, one of his 1905 papers, so in 1905, Einstein published 5 papers, 4 of which were absolutely revolutionary. So this was the year where he published the paper which he first introduced the theory of relativity, the year that he published the paper where he first introduced E equals mc squared. He published the paper for which he would ultimately win the Nobel Prize on something called the photoelectric effect. And he published this paper. This paper on Brownian motion explained how, if you imagine that what was happening to these particles of pollen was that there were much smaller particles that were bombarding it randomly in different directions, and that sometimes there'd be more of them on one side and sometimes more on the other, and that explains what would make it move one way and then the next. That in fact, using that assumption, you could model the statistical properties of the paths that the pollen would follow. And so here's an example of that kind of path. And what you can do is, if you start with the molecule or a particle of pollen in one place, say you've got something like a petri dish and it's just in one location, you can ask the question, if this is the process that's making the pollen move, what's the probability that you're going to find the pollen in any particular region of the petri dish at any particular time in the future? And so what you're able to derive is a probability distribution over locations that this pollen particle could occupy. And more, you're able to derive how that probability distribution changes over time. And so this allows you to make predictions about where this thing is most likely to be later on. Now, in fact, this argument turned out to be essential to the experiments about 5 years later that established once and for all the existence of atoms. Up until the early 20th century, the idea that there existed invisible atoms, that the rest of matter was composed out of, was hugely controversial. Leading physicists at the time thought that this was speculative metaphysics and couldn't possibly be experimentally tested. Einstein gave a clear empirical test for the existence of atoms. If there are atoms, observable particles will have this statistical feature. Okay. What Osborn realized was that the statistical properties of stock prices were strikingly similar to those of pollen particles. What he realized in particular was that stock prices changed as if the percentage change at each time was random in one direction or the other, as if the thing were being buffeted, the price itself were being buffeted by outside stuff. And he gave a model of how this would work. The picture was supposed to be that at any time, the price is supposed to reflect all available information. New information could come in. That new information could be good for the price of the stock, or it could be bad for the price of the stock. But it was essentially random how that was going to work, because you don't have any of this information available yet. So it could be, you're ignorant about whether it's going to be positive or negative. The idea is that that new information plays the role of these atoms that are making the price, specifically the percentage change in the price, bounce around. This allowed Osborn to derive a probability distribution for future prices of stocks that he could then go back and test against actual changes in prices of stocks. More importantly, it allowed him to predict how that probability distribution would change over time. So he could say what the probability was that a share of a particular company would be worth X dollars a year from now, what the probability would be that it would be worth the same amount 2 years from now, what the probability would be that it would be worth more than a certain amount some number of years from now, and so on. Okay, now, Osborn published this paper. He published a number of follow-up papers on the topic, in each of which he tried to poke holes in his own theory, gave a lot of evidence to back it up, and eventually it got picked up by people working in mainstream financial economics. Not yet in the financial industry, but economic theorists who were working on understanding the statistics of stock prices. Now, what Osborn was not able to do was figure out how to use any of this information to feed those twins. In fact, he believed that he had proved once and for all that there was no way to get an edge on financial markets. After all, he had proved that price changes were random. There was no way to know whether the stock was going to go up or go down. Okay, so, perhaps unsurprisingly, Osborne himself wasn't the one responsible for changing how financial practice worked, because the investment banks weren't all that interested in hearing how you couldn't make a profit. Okay. That last piece was provided by someone else, a man named Ed Thorpe. And so Ed has, in fact, just written an autobiography called A Man for All Markets, which is just wonderful. He's a fascinating person, a fascinating story. So stepping back a few years, right? So we were just in 1959 when Brownian Motion in the stock market was published. In 1955, Ed was a graduate student in physics at UCLA. And he and a group of friends gathered together at the grad student co-op. They were chatting about Las Vegas. Right, so Las Vegas had just opened. It was an oasis in the middle of the desert, just a few hours outside of Los Angeles. And these physics grad students, as physics grad students are wont to do, thought, we're pretty smart. Maybe we could figure out a way to beat these casinos. There's a lot of money there. We've got to be more clever than whoever's running these things. Maybe we can find a way to get an edge. And so they discussed various games that were offered at the casino and thought about different ways that they might beat those games. One of the ideas that was floated was roulette. Now, this was quickly dismissed by most of the people there, because after all, everyone knows where the ball lands on a roulette wheel is completely random. There's nothing that you can do to get an advantage. Or so they thought. So Thorpe had this idea that, well, look, one of the things that physicists are good at is figuring out how a ball rotating around a spinning wheel is going to behave over time. He thought, you can write down some differential equations, which you could solve, that should tell you how this thing evolves. Now, it's not going to be perfect because there are randomizing devices on a roulette wheel that are designed to make the thing bounce around. But he thought, you could still probably come up with some way of telling where the ball was most likely to land. Right? Maybe you could say it's more likely to end up in this quadrant than in this quadrant on the other side of the wheel. Now, of course, actually doing this in practice seemed pretty far-fetched, because you would have to solve these equations. You'd have to figure out what the initial position of the ball was, and the initial velocity of the wheel, and the initial velocity of the ball relative to the wheel, and somehow plug all of those initial conditions into your differential equations, and then come up with a solution, and only then go and make your bets. Now, of course, the game will have moved on by then. But he thought maybe it would be possible to build some sort of machine, some sort of computer that could do this. Of course, this was a radical idea in 1955. The idea of a computer small enough that you can even carry it into the casino was pretty extreme. But he had this idea, and he kept thinking about it. Jump forward to 1959. Finished grad school. He's about to move to MIT to take up an instructorship there. On his way cross country, he decides that he's going to go to Las Vegas for the first time, in part because he wants to look at these roulette wheels and think a little bit more about this idea. As he's getting ready to go, a friend gives him a paper written by a group of Army scientists. Now, what this group of scientists had done was worked through all of the calculations concerning possible hands of another game, blackjack, 21. Okay, so blackjack is a game where there's a dealer and a player. Cards are dealt to both. The player keeps asking for more cards with the goal of getting a higher number than the dealer is able to get without going over 21. Right, so the idea is, in effect, to either get as high as you can without going over 21, or somehow force the dealer to go over 21 instead. And so there are many different possible configurations in this game, but it's a finite number. And the army, using computers, which in the late 1950s usually meant people with pencils, worked out all of the probabilities associated with all of the possible hands. And using that information, they published what they claimed to be the optimal strategy in blackjack. Now, I told you, right? Military science after World War II was working on all sorts of stuff, right? Including this. Okay, so Thorpe took this paper. He wrote down all of the things you were supposed to do on an index card, which he dutifully took to the blackjack table and sat down and read off and played exactly the way that this paper had recommended that he do. And he lost all his money. It was a losing strategy. They knew it was a losing strategy, right? It was a strategy where, in the long run, you would expect to lose all your money, and indeed he did. But it was a strategy where you lose your money more slowly than other strategies, which, when you're a graduate student, is a pretty attractive proposition. And so he realized that, yeah, look, this seems to be working. I'm losing my money, but everyone else is losing their money faster, so there's something to this. But he also realized that the army had made a kind of mistake. There was an assumption that had gone into their model that wasn't accurate in practice. That assumption was that every hand of blackjack was statistically the same as every other hand. In effect, they had assumed that every hand started with a new deck. But Thorpe realized that just wasn't the case, at least back then. What would happen is the dealer would start with a deck, would deal out a hand, that hand would get played, the cards would be swept to the side, and another hand would be dealt out. Now, of course, if all of the aces showed up in that first hand, that's going to substantially change the probability of getting blackjack in the next hand. And that should affect your betting behavior. That should affect the strategy you adopt. And Thorpe realized that if you could keep track of what cards had been played, you can perhaps get an additional advantage. Okay, and so he left Las Vegas, now interested in blackjack rather than roulette. Went to MIT, got time on their supercomputer, which really was a machine, not people with super pencils, and was able to prove for the first time mathematically that, in fact, there is a winning strategy at blackjack if you count cards. Okay, and so he wrote a book called Beat the Dealer, in which he explained how this worked. The book was published in 1962. It was a massive bestseller. He had not only come up with a strategy, but he had tested it in Reno with some money provided by the mob. There was an exciting story in addition to a get-rich-quick scheme. It had all of the pieces for a massive bestseller. Now, Thorpe was pretty interested in this. He thought it was a fun thing to do. But he continued to be interested in this kind of problem generally, coming up with ways in which you can identify a situation where you have an edge. Now, that was part of the strategy with blackjack, right? Figuring out that really there were things that you could do in each situation where the probability of you winning in the long run was positive. But there's another problem. Suppose that you figured out how to win. You figured out how to get an edge in a game like this. What should you do? Think about it this way. Suppose someone came and said to you, I've got a coin that will land heads twice as often as it lands tails. And I'll give you even money every time you bet heads. That sounds like a great bet. How much of your money should you be willing to put up? Well, you should certainly put up something because you're going to win more often than you lose. But you don't want to put up everything because you're still going to lose a third of the time. So presumably you want to put up some amount of money in between everything and nothing. And in fact, there's a mathematical theorem that says what percentage of your total bankroll you should be willing to bet under any particular circumstances in which you know that you have an edge. Right? So in addition to coming up with the edge, there was this whole strategy for how to use the edge to actually have a gambling strategy that could make you money. Okay, and so Thorpe was interested in finding other ways of applying this new know-how. And so around 1964, flush with cash from both the blackjack and the blackjack book, he decided that he was going to turn his attention to a bigger casino. He was going to see if he could find a way to apply these ideas to the financial market. He very quickly came across Osborne's paper and thought, this is exactly the kind of information that I need. I need to know information about the future probabilities of various things happening in order to apply this kind of strategy. But he, like Osborne, realized that if you're going to use the kind of information Osborne has provided, and you're just going to trade stocks, you don't actually get an edge. You just find that it's equally likely for you to make money as to lose money. But what Thorpe realized that Osborne didn't was that there are other ways of trading in the financial markets. Rather than just buying and selling stocks, you can buy other products. In particular, a product that was available at that time was something called a warrant. Now, warrants are effectively the same as options. They weren't traded on an exchange because there weren't exchanges yet for options. Instead, they would be usually traded with the company that the warrant was on in the first place. But what a warrant did was, like an option, for some price up front, it gave you the right to buy a particular asset at some fixed price called the strike price at some time in the future called the expiration. And what Thorpe realized was that an option is a kind of bet. It's a bet that the underlying stock, the thing that you're buying the warrant on, will exceed a certain price in a certain amount of time. How much the thing ends up being worth then depends on by how much it exceeds the price. And so this leads to a simple mathematical problem. How much should you be willing to pay now for the right, but not the obligation, to buy something else at a fixed price in the future? Now, in order to solve that problem, the input you need is precisely the information that Osborne had provided. You need information about what the future probabilities are that the underlying asset will take various prices in the future. Okay. Now, when Thorpe figured this out, he immediately did the same thing that he had done with the card counting strategy. He wrote a book, even gave it the same name, basically. He called it Beat the Market, follow-up to Beat the Dealer. He co-authored it with his colleague. He was at this point at UC Irvine. Co-wrote it with a colleague in the economics department in Irvine. And it was a flop. Now, there's a huge irony here, right? Because nowadays, you come up with some innovative new trading strategy that's guaranteed to make you money. You don't tell people about it. You trade with it, or maybe you sell it to someone who has more money who's going to give you a piece of the action. Thorpe, that didn't even occur to Thorpe. He didn't have that much money. He was interested in the math. It was fun. Thought people would be interested. This was so innovative in 1967, I think, when the book came out, that no one was able to recognize what had been accomplished here. Very few people read it. Of the people who read it, very few of them appreciated what was being offered. Now, one person who did appreciate it was a man named Jack Regan, who was a broker-dealer in New York. He called Thorpe up and he said, look, I understand the financial industry. I know how to actually execute these trades. I know the ins and outs of the community. Let's team up. You do the science part on the West Coast, figure out strategies like this. I'll do the trades on the East Coast. They called the company Princeton Newport Partners. It was the first quantitative hedge fund in the modern sense. It was started in 1969. Over the next 20 years, while the company was active, they made 20% a year every year. They had 2 down quarters the entire life of the company. It was enormously successful. Thorpe eventually even had to quit his job as a math professor order to focus on this full time. Okay. Now, the success of Thorpe's company and the kinds of strategies that were described in Beat the Market and that were demonstrated as effective in practice with Princeton Newport partners began to change the way people thought about how mathematical methods, these methods inspired by and developed by work in physics and by physicists, could be useful. But that's not the end of the story. There's another series of things that happened just a few years later that really sealed the deal. So, 3 things. One, in 1973, an economist at MIT named Myron Scholes and an applied mathematician working as a consultant in Boston teamed up and published a paper in which they presented a solution to the options pricing formula that was formally very, very similar, essentially equivalent to the solution that Thorpe had come up with. But they presented the argument in a way that was much more familiar to economists. In fact, their reasoning to get to this solution was quite different from Thorpe's. And so the result of this was that there was now a document out in the world that people in economics departments, people who worked at financial institutions could read that was written in their language. Another thing that happened in 1973 was that the first US-based options exchange opened in Chicago. So previously, Thorpe had been trading these warrants. There wasn't a big market for them. They weren't systematically traded or priced. There were a lot of inefficiencies. There were a lot of illiquidity in that market. Suddenly, there was an exchange, which meant that there were a lot more opportunities to trade these things and a lot more interest in trading these things coming from larger financial institutions, which meant that figuring out how to price them, figuring out how much they were worth, was suddenly a much more pressing question. There was a third thing, though, that happened. So 1969, the year that Thorpe started Princeton Newport Partners, was also the year that the first Apollo mission to land on the moon did so, right? So the year that the US landed on the moon. That year, funding for NASA was 4% of the US federal budget, an enormous amount of money. The following year, it plummeted. That money, the space race had been won, that money was diverted to Vietnam. This meant that a generation of physicists who had been funded through graduate school by this high level of science funding at the federal level in the US graduated to find that all of that money was gone. And all of the jobs that had been promised that were going to be funded by that money were also gone. So it wasn't instantaneous, but there was suddenly a generation of largely unemployed and underemployed physicists who were looking for new ways to take their training and find their way in the world. At the same time that the first options trading exchange opened, at the same time that these innovative new ways of applying mathematical methods to trade derivatives, options are an example of a derivative, became available and better known. And it was that mix of things that gradually led this generation of physicists to accept jobs at Wall Street banks, for Wall Street banks to think, hey, this is the kind of person that we need to hire. And that's when this culture shift happened. Okay, now I'm going to come back to the morals of that story. But I want to talk now about a more recent development in both in physics and the application of ideas from physics to finance. Because I think that what we've seen so far is some interesting history of how physicists were able to think about markets differently from people with traditional training. And they were encouraged to do so, given sort of broader historical and political context. But we haven't really seen examples where ideas that seem distinctively physical ideas as opposed to ideas from mathematics or ideas from statistics applied in a way that physicists would apply them, were used. Okay, so I want to turn to much more recent stuff. So physics has really only been understood, I think, in the last 30 to 40 years. The physics of critical phenomena. So a critical phenomenon can be thought of as a kind of a phenomenon in which there's a kind of transition between two different states. And so some phase transitions are like this. Not all phase transitions are critical phase transitions, but some phase transitions are. And you can think of that as being your picture, where you have two qualitatively different states. And a system can transition between those two qualitatively different states. So one example is a state where something is magnetized and a state where it's not magnetized. And so there are some materials where, as they get colder, they become very strong magnets very quickly. Other examples include things like avalanches, things like earthquakes, where you've got two different states, and at the transition point, there's a kind of discontinuity. There's a kind of extreme behavior that can happen. Okay. Now, the interesting thing about, or one of the interesting things about the physics of critical phenomena is that the way in which we ordinarily think of events being caused isn't really appropriate. So think about an avalanche. You have snow gradually accumulate on a mountain. During this gradual process, you can do all sorts of things. You could add more snow, animals could walk around, you could yell all you like, you could clap, you could stomp your feet, whatever you like. Not going to make any difference. But gradually, as the snow accumulates, the system becomes more and more sensitive. So that these sorts of events that ordinarily wouldn't have any influence at all can begin to get amplified. Right? So that under some circumstances, merely yelling is sufficient to cause an avalanche. Now, the thing that's important here is that the event that sort of precipitates the avalanche or triggers the avalanche isn't really responsible for the avalanche in the sense that there are a million different things that would have been equally good for producing the avalanche under those special circumstances. But under other circumstances, none of those things would have had any effect at all. Now, the idea is that this is an idea that I think was first developed by a French physicist named Didier Sornet, who's now at ETH Zurich, working with many, many collaborators, both in the financial industry over the course of the last 20 years or so, both in the financial industry and in physics. He's argued that we should understand financial crashes as examples of critical phenomena. Now, he's actually developed a pretty detailed mathematical theory of how critical phenomena of this particular sort work, that he's applied not just to market crashes, but also to, for instance, earthquakes, to he started working on this in the context of the European Space Agency. So there were these pressure tanks that would periodically explode, and they wanted to know how to make them not explode, or at least to know when they were going to explode. And so he developed these methods there and then began applying them elsewhere. And along with this detailed mathematical theory is a series of predictive measures, ways in which you can anticipate when a crash is likely to occur. Now, I want to step back from those details and just observe that there's something, I think, deeply insightful about the idea that we should understand market crashes as critical phenomena in the sense that I've already explained. This is insightful for the purposes not just of ordinary investors, but also for regulators. Because if what I've just said about avalanches applies to market crashes, then there's something futile about asking the question, what caused this market crash? Now, I just want to emphasize, that really is a question that gets asked all the time. So, for instance, there was this very unusual market crash in May of 2010 called the flash crash, right? And so the Dow Jones Industrial Average dropped 1,000 points in a matter of seconds and then rebounded almost as quickly. There was a lot of consternation about how something like that could happen. And the financial regulators, the SEC and the CFTC, wrote a joint report in which they detailed each individual trade that had happened in the lead up to the crash and made the argument that it was this particular company based in the Midwest part of the US that had executed a trade using an algorithm that was poorly designed. And what this algorithm did was it was trying to sell a particular asset. They were trying to sell a lot of it, and it was designed to sell at a particular percentage of the total trading volume. So they sold a certain amount. This looked like a pretty big sale. Some other algorithms thought, oh, people are selling. I should do whatever I'm supposed to do when people start selling, and that increased volume. And so the first algorithm said, oh, volume's gone up, I can sell more. Everyone else said, oh, well, people are really selling a lot right now. We should get out of the market. And so that increased volume and also drove down price. The first algorithm thinks, oh man, volume is great, I can sell all of this stuff right now. And this quickly snowballed, pun intended, and the market crashed. Okay, so that seems like a fine story, except the same algorithm had been used about a dozen times before without causing a crash. And so saying that it was somehow this algorithm that caused the crash seems to miss the important thing about what made this time different from other times. Now, there's a further rub to this, which is that 2 years ago, there was an individual trader arrested, charged with, among other things, causing the flash crash. What this individual was accused of having done is something called spoofing. So spoofing is when you offer a trade at a particular rate and then don't execute it, with the goal of changing market prices in a way that you can then immediately exploit. It's illegal. It's fine to arrest this guy. But suggesting that this guy was responsible for the flash crash is again misleading. In fact, he had executed the exact same spoofing strategy over 200 times before. So once again, it seems like the salient question isn't what about this guy caused the crash? In the same way that the question with the avalanche shouldn't be what was it about your clap that made the difference? It wasn't your clap that made the difference. It could have been any number of things once the mountain was primed. Once the mountain had evolved into this critical state where small perturbations could be hugely amplified. The idea is that market crashes are the same, that the right way to understand market crashes is as a systemic event. It's the sort of thing where markets evolve into a state where small changes have outsized effects. I think that that's an important insight that should change the way regulators think about what crashes are about and how to prevent crashes. It's really about systematics, not about identifying individual actions for enforcement. Okay, so to conclude, I want to step back and address some of the philosophical questions that I started with. So let's first return to the Monty Hall problem. What's really the moral in the Monty Hall problem? Well, it seems to me that the real moral is that we have a kind of compromised ability. We're very bad at reasoning under conditions of uncertainty. Our guts are unreliable guides to probabilistic situations. We develop mathematical tools to help overcome this inability to reason intuitively about probabilities. Now, the Monty Hall problem is as simple a problem as you could hope for. Deciding how much an option should be worth is a far more complicated problem. Still more, figuring out how to do, for instance, risk analysis of an entire financial industry is a much more difficult problem. If we can't intuitively solve the Monty Hall problem, it's hopeless to think that our guts are going to be reliable guides to the bigger problem. For that reason, it's essential, I think, to make use of every crutch we can come up with. Every mathematical tool that we can come up with is of value to us for the purposes of reasoning about these sorts of situations. Of value to us on the one hand as investors, but also of value to us as policymakers, as regulators, as people who are interested in having well-run markets with minimal systematic risk. Okay, so the idea that some of the critics of mathematical modeling in finance that I was discussing at the beginning of the talk floated that there was something fundamentally flawed about the idea that we should use methods from physics and elsewhere in the mathematical sciences to understand markets, I think is as backwards as could be. First of all, because one thing that I hope is clear from the examples I've presented is that there's not this, what's going on here is not that anyone is imagining that individual investors are like billiard balls or like stars or something like that, that we're somehow assuming that people have deterministic law-like trading behavior. That's not what's going on. Rather, we're using mathematical modeling methods to study the large-scale statistical behaviors of investors as a whole. And that's an important and useful thing to do. But there's another side to it, which is that every mathematical model that you can possibly come up with has assumptions built in. We assume things about how markets work. Those assumptions are sometimes very good, they're sometimes very weak. They're the sorts of assumptions that you would expect to hold all the time. When those assumptions do hold, the inferences you draw about markets from the models are going to tend to be reliable. You should trust the models. But you also have to be attentive because sometimes those assumptions will fail. And in many cases, when they do fail, they fail in recognizable ways if you're paying attention. Now, this is something that I think is second nature to the people who actually develop new mathematical models. You talk to someone like Ed Thorpe about how he understood the models he was developing, it's completely clear that he knew when they would work, when they wouldn't. He was very careful to apply them under circumstances when he knew them to be reliable and not otherwise. He was very cautious. But when you step back from the people who design these things, and the models get integrated into a much broader practice, where for many of the people who are making decisions based on these models, what goes in is quite opaque. Then you can begin running into problems. And so there is a sense, I think, in which in the 2008 crisis in particular, there was a problem with the application of models. But the problem wasn't with the models themselves. It was with the way in which the models had been integrated into a broader system in such a way that it was very difficult to recognize what was being assumed by now the system as a whole. And so when those assumptions began to fail, in particular, they began to fail when housing prices started to decline in 2006, the models that were being used, the equations that were being used to price assets that had become essential to the world financial system became unreliable. Some people noticed. Some people made a lot of money in 2007 and 2008. But the rest of us suffered. The rest of us suffered because the system as a whole wasn't in a position to evaluate the role that these assumptions were playing. Thank you.
Very good. All right, we'll open the floor to questions, and why don't we go to Aiden?
Okay, so this is not a very, it's not going to be a very, a mathematical or that sort. Why is Wall Street called Wall Street?
I don't know. Maybe there was a wall.
Oh, that's very good. All right, let's jump online. A few good online questions here. This one: what's the most effective way to get into the career field of quantitative analysis, a quant? Through physics, through finance, through statistics?
Well, it seems to me that really there are two questions here. One question is, what kind of training should you try to have if you really want to be effective in this field? I was asked this question, actually, once I was on stage. It was me, Ed Thorpe, and managing director at PIMCO, which is a huge mutual fund management company. And they asked me how to become a quantitative analyst. I'm a philosopher. These guys, but what my answer was, look, there are a lot of ways of getting trained in what the equations are, what the models that get widely used are. Some of those ways of training, though, emphasize taking the models in the textbook, figuring out how to program a computer to apply them, and going from there. And that's useful, 99 days out of 100. But that doesn't put you in a good position to ask this further question that I was suggesting was of the utmost importance at the end of the talk, which is, what are we assuming when we derive these equations in the first place? And under what circumstances can we expect these models to be effective? And for that, I think that really training in the basic sciences. It's still the case, I think, that training in physics, and in some cases in mathematics, is going to be the most helpful to you. Now, if what you're ultimately interested in is getting a job, you should ask someone who's in a position to hire quants.
Thank you. Let's go in the studio.
Okay. I approached this problem that you're talking about through cybernetics and policymaking as an economist and econometrician, having worked for Barclays and having the dubious distinction of making Barclays over 500 million in the space of 1 week, of which I received nothing. My point is that Jan Tinbergen, a famous economist, basically designed a system in which you have essentially a system of equations in which you have the number of variables and you have a number of variables and number of parameters. And the notion was that as long as you had more instruments than variables to control, you could actually come up with a control system, which essentially actually developed into cybernetics and its theory of cybernetics. Now, when you come into physics, you have a situation in which the physicist does not have 1/100th of the information that an economist has. I'm a Bayesian economic theorist, a mathematician. Essentially, Bayesian economics is different from the physics statistics of what we call frequentist statistics. So you're using an entirely different approach. Bayesian statistics I found as far more effective as particularly if you can set out your system of equations in arriving and narrowing down the errors in your system, just like you minimize errors in production when you're manufacturing cars in Japan.
So there are, I think, a lot of interesting things to respond to here. First of all, I am a Bayesian myself. A philosopher. We're also mostly Bayesians, I think, these days. And so I'm sympathetic to the idea that many physicists are trained to use some statistical methods that are probably not the best statistical methods. I should be careful. On the other hand, the kinds of applications that I'm describing here, the kinds of things that I'm talking about, both in the book and in the talk, are a little bit more. So it's really about how a particular way of thinking about the world ended up being fruitful, not about how the particular things that this group of physicists were trained to do are the right ways of doing things. And so just as an example, Jan Tinbergen was trained by a physicist. His PhD advisor was Max Ehrenfest, I believe, the distinguished one of the fathers of quantum theory. And so, in some sense, even this tradition in economics comes out of a certain kind of training in physics. that's the kind of connection that I'm really trying to emphasize here. I think that once, there's a great online comic called XKCD, and one of the comics that was published on this site has a physicist talking to someone in another field that says, well, why don't you just model this as whatever thing from physics with these two tweaks that I just came up with? I don't even understand why your field has a journal. And there is an attitude that many physicists have that, look, we know how to do this better than you do. And that's not really what I'm trying to endorse here. I'm not saying that the economists should just start doing things more like physicists do. I'm rather trying to trace how particular kind of mathematical modeling methodology gradually came out of other mathematical sciences and moved into finance and into economics through people like Tinbergen and Paul Samuelson and Irving Fisher, all of whom had training in physics originally.
Thank you. Yeah, at the microphone.
Thank you very much. I've really enjoyed the talk. In the last 3 months, two things have really happened. One is the stock market has hit a record high, I think past 20,000. Just a couple of days ago, it's come down a bit since then. And two, I think it's fair to say the administration in the United States has become a lot less predictable. Mm-hmm. We really have no idea if there's even going to be a trading relationship with the United States and the rest of the world, and there are various other changes happening at 3 o'clock in the morning on Twitter. This sounds incompatible to me. Can you comment on how these mathematical models struggle or how they perform under these sorts of environments? Thank you.
Yeah, so there's an irony here, right? Because it was a tweet that Justin Trudeau produced over the weekend that all of the Syrian refugees that the U.S. was turning away wouldn't get settled in Canada, and then that didn't happen. People tweet up here too. I've heard threats of making the U.S. pay for a wall of some sort.
It was a tweet, not an actual law. So it didn't
Yeah.
actually mean anything.
Okay, so I actually think that this is a really important question. There's been a lot of analysis recently saying that the reason the market has responded so well over the last 3 months is because many traders are thinking, oh, this new administration is going to be good for business. They're going to do all of these things. There's going to be a lot of stimulus spending through infrastructure projects. There's going to be massive tax cuts, which are another kind of stimulus spending. All of that is going to drive up corporate profits, and therefore we should price that in to current prices in the stock market. Along the way, people, I think, are suppressing some of the less good for business policies that have been proposed regarding, for instance, international trade. And my guess is that there's a kind of cognitive dissonance going on here. People really don't know how to take all of the things that the new administration in the US is saying they're going to do and process them into a coherent narrative that tells you how you should trade. Now, there's a theory that I criticize to some extent in the book due to a derivatives trader named Nassim Taleb, who wrote a very influential book called The Black Swan. Now, one of the things that he says is that, look, mathematical models are completely useless because they're never going to let us predict black swans. Now, I criticize the part where he says mathematical models are completely useless, and I point to some cases, like this work by Didier Sornet, where at least some market crashes look like they may well be predictable. But it's still the case that the models just don't include stuff that's never happened before, that's unlike anything that's ever happened before. And so the right way of thinking about what's going on right now is that we see a big, slow-moving black swan coming right for us, and we have no idea what to do. And you know.
Let's go to the microphone one more time.
Yeah, I really enjoyed your talk too, and just a little background, my PhD is in semiconductor device physics, And around 92, 93, I saw the light and started applying all that to financial theory. So I guess that makes me some sort of quant in the way you're talking about. I was trying to think of an example, because I'm fascinated by your concept of looking for where the assumptions fail. And the one that comes to mind is the long-term capital management hedge fund based in Connecticut that had 2 Nobel laureates on staff, were doing amazing models in the bond market, and in 1998, I believe their value went negative. And they had to be rescued by the Federal Reserve Board. Do you know what assumptions failed in their models in that case?
Yeah, so in fact, I think the situation with long-term capital management was there was a particular assumption that they were making, which was that the ruble wouldn't collapse, and it did, and that caused huge problems for them. But there was a deeper problem, which was their strategy was one where you would make fractions of a penny on a dollar. And in order to make real profits, they needed to leverage up their actual holdings by a factor of 60, 70 or more. That just makes you incredibly sensitive to tiny problems with your models. Now, they'd won Nobel Prizes. They thought, look, we've got this all figured out. And I think that there was a kind of hubris in their particular application, a kind of hubris that frankly shouldn't have been there, because the same models had failed, not in exactly the same way, but in ways that I think could have been used to anticipate the problems that long-term capital management faced in the 1987 crash. Ultimately, what happened there was also a failure model. So in particular, there was a product known as portfolio insurance that was sold in the lead up to the 87 crash that was marketed as the sort of thing that would literally give you an insurance policy. Your portfolio couldn't drop below a certain floor because you had bought this insurance policy. And you'd pay some premium for it. This was effectively an option that gave you the right to sell at some fixed price on your whole portfolio. Now, these options were constructed in a particular way using the Black-Scholes model. Built into that model is the idea that there are no transaction costs and markets are perfectly liquid and you can trade instantaneously and all that. Now, trading instantaneously in perfectly liquid markets are exactly the things that you don't have during a market crash. And so this was a product that was designed to do something under precisely the circumstances under which the model underlying the product couldn't be trusted. And I think that Fisher Black wrote this wonderful paper called The Holes in Black-Scholes, published in a book called From Black Holes to Black-Scholes, that is difficult to get your hands on, but is worth the investment, where he lays out all of the problematic assumptions in the Black-Scholes model and talks about how some of them can be patched up, but just says, look, this is going to work sometimes. It's not going to work under a whole lot of circumstances. And somehow that message seems not to have been fully digested by the people who were running long-term capital management.
May I ask an addendum question?
Sure.
Thank you. The 1929 crash can largely be traced to banking problems that originated in Vienna in Austria. At least many people maintain so. And if you look at the fractional banking reserve requirements, the banks in Europe, many of them have very high levels of like loans versus their equity, levels that would not be allowed in Canada, for instance. Mm-hmm. Do you foresee, particularly considering a lot of the problems in the pigs nations, as they call them, that there could be a crash lurking amongst the European banks?
I don't know.
All right, I'm going to go to the last question online, so you can ask your question in the atrium after, if that works. All right, so let's go one last question online. It's a good one, and because I have the microphone, I'm interested in the answer. I'm definitely going to go with it. Do you think there are other areas in human endeavor where physics might not traditionally have been employed, but where it might be used to make big progress, such as social issues or humanitarian crisis? Any thoughts?
Well, I think that, first of all, actually quite close to this, there's an entire field now called econophysics. I've been talking about finance. Finance is, in some sense, a subfield of economics. But the ways that people think about economics and the ways that people think about finance are really quite different from one another. Now, it's interesting because the examples I've given here are all cases where ideas that came out of physics got quickly absorbed into financial practice. Econophysics has not been absorbed into economics. It's really a kind of semi-autonomous discipline. But what's happened is that people have begun trying to use modeling methods, in many cases much more robust analogies to the actual physics than in the cases that I've described here, in order to model a very wide range of social phenomena. And so things like how money gets distributed through a population. So there are a group of people who work on what's known as the thermodynamics of money, and they argue that the reason you get the particular distribution of wealth that you see in most, at least Western societies, is as a kind of statistical effect that arises from just people randomly meeting and trading with one another. Economists hate this, and they've got some good reasons for hating it, but it's a case where a question about global inequality is being addressed by looking for a kind of minimal model from physics that could account for the behavior that's observed. I think the strategy is to say, if all it takes is this to get inequality of this sort, then any policies that you're going to propose that don't address this basic kind of dynamical effect probably isn't going to solve the problem. So I think, even as close as economics, but you get these sorts of things happening in sociology as well, mathematical approaches to evolution. There's a whole area of biology called quantitative biology that I don't know very much about what they do, but they have conferences in Hawaii, and my wife keeps going to them. And apparently it's all physicists. Yeah.
Very good. Ladies and gentlemen, Dr. James Weatherall.